Good afternoon, everybody. So I'm going to be talking about a proponent model for directivity based on the Cho and Young's and WS3 ground motion prediction equation. This should seem very simple after this morning and the last couple days of salmons. I hope, at least. If your brains are still working after all of that, it'll seem simple at least. So some of you have probably seen this presentation before, and this all sort of started with a concept maybe a little over a year ago, which is sort of that we expect there to be locations around a specific rupture that experience both positive and negative directivity effects more frequently than other locations. So if you can think of like a strike-slip fault, and a rupture on that fault, off of the ends of the rupture, those sites would experience both a whole bunch of forward directivity if the hypocenter was located far from them and the rupture was progressing towards them, and they would also experience sort of the opposite extreme of what we call, for lack of a better term, negative directivity. So when the hypocenter is close to the site and most of the fault is rupturing away from it. So that would be an example of a location where we expect there to be large differences in the directivity effects. Whereas if you were off of the sides of a fault, maybe you're only seeing sort of intermediate directivity effects all the time instead of the two extremes. So the idea was, can we develop a simple model of this variability, sort of an additional standard deviation, that you could then tack on to existing published ground motion prediction equations in order to account for directivity. So this was meant to be a hand-wavy way of accounting for directivity while other models are still being developed that hopefully would account for it in a better way, a more quantitative way, sorry. So how would we go about developing such a model? Well, we can think of the standard deviation at a specific site around a rupture in sort of three different parts, where the first part of the standard deviation is for just an average site where the effect of directivity is not included in the standard deviation. So instead, it's included in the mean of the ground motion prediction equation. So this would be for a regression like Cho and Young's 2013, where there's a directivity parameter in the mean. So it sort of has, it has a standard deviation that doesn't have the effect of directivity in it. So this is what you'd sort of start with when you're looking to add more standard deviation on. This would be your base case, the bottom line. You would then want to add on the difference in the standard deviation for an average site where between including and not including the effect of directivity in the standard deviation. So this would be the difference in running a regression between having a directivity term in the mean and then not having a directivity term in the mean. So if you took directivity out of the mean, we would expect the standard deviation to go up because there's variability in the ground motion that you're no longer predicting with your mean. So this difference was estimated by Bob Youngs for the Cho and Young's relationship. There's the cursor. So on here we have period down on the bottom, and then the y-axis here is the ratio of the intra-event standard deviation with including the directivity in the mean or not including it in the mean. So we can see out here at long periods, when you take the directivity out of the mean,
on the call.
good, standard deviation goes up. So then the last part is the difference between the standard deviation at a specific site and your average site. So this is the variability that you would get by randomizing hypocenters all over your rupture. So and then you're calculating the difference. It's okay. So it's the difference between a ground motion, sorry, lost my focus. So difference between the ground motion at a site I and an average site when you're randomizing hypocenters on a rupture where directivity is included in the ground motion mean. So here you're accounting, so you're going to get both above and below median ground motion by moving the hypocenter around. So how do we go about calculating such a thing? This isn't something that's been generated before that comes out of the regressions. We have to do some forward modeling to do it. So what I did was generate a set of fault geometries, both for strike slip and reverse faults, for the strike slip between magnitude 6 and 8, and for the reverse between magnitude 6 and 7.5. And then for each of those ruptures, I chose a set of sites with 1 kilometer spacing in racetracks around the ruptures at rupture distances of 1, 5, 10, and 20 kilometers. In terms of the hypocenter location, the hypocenters along strike are clustered towards the middle of the rupture. And for both the reverse and the strike slip faults, they, in terms of down dip, they're clustered more towards the bottom of the rupture, about 2/3 of the way down. The standard deviation of the ground motion then, by randomizing all that hypocenters, can be calculated by taking the difference between the ground motion for a specific site and a specific hypocenter, and then subtracting off the ground motion from an average site, from an average site. And we can break this down into 2 parts. It's easier to think of it that way, where the first is the bias at a specific site with respect to the average. So if you took if you take the racetrack at 5 kilometers, there'll be an average ground motion at that along that racetrack. And then each of those sites will be biased either high or low with respect to that average, depending on if they're seeing a whole bunch of forward directivity most of the time or reverse. So that you get that bias. And then around that bias, they also see variability, right? So even if they're seeing more frequently forward directivity, so they have a high bias, they're not always seeing high forward directivity. They're going to see some low and some median. So you get a variability about that bias as well. Calculation. Okay. So I went ahead and did this forward modeling using the Cho and Young's ground motion prediction equation. And I'm going to show you guys some figures of the mean bias and the variability about that bias for 3 seconds for the strike slip magnitude 6 through 8 and the reverse magnitude 6 through 7.5. And because the difference between either including or not including the directivity and the mean affects the standard deviation very little, then it's this forward modeling that really controls the results and controls what you would add to your published ground motion prediction equation. Oh, and I just wanted to note too that for the Cho and Young's directivity model, the peak effect, because I'm just showing you 3 seconds, the peak effect is at a magnitude 6.5. But as you go out to longer periods, then the peak effect will move out to higher and higher magnitudes. So you'll see a peak here at around a magnitude 6.5, but that would change depending on the period you were looking at. Okay, so you're going to see a whole bunch of figures like this. Up on the top, so this is for a strike slip magnitude 6 event, or strike slip magnitude 6 rupture geometry, I should say. So this black line in the middle is the surface projection of the fault. And then there are points around this at racetracks of 1, 5, 10, and 20 kilometers. So the space in here is not completely filled by calculations that I've made, which is why it looks a little strange. The top is the mean difference, so the bias at a particular site with respect to the average at that distance. So every distance, every racetrack has an average of 0. So unbiased. And if you added up all the biases along your racetrack, you get 0, if I've done this right. So yes, along the X and Y axis there are just kilometers. So the top is the mean difference, and in the upper right-hand corner, in case you can't see the scale, it goes from negative 0.3 to positive 0.3. And the bottom figure is for the additional standard deviation, the additional variability that's about that mean bias. So for this magnitude 6 at 3 seconds, the additional standard deviation varies from 0.02 to 0.18. And this standard deviation, you don't add this to the standard deviation that you get from a ground motion prediction equation. You'd have to SSRS it in. So 0.02 is effectively 0. And up to 0.1 or 0.15, you wouldn't even notice a difference depending on the standard deviation. So this is the magnitude 6. Magnitude 6.5. So still the peaks for these, for the strike slip case, you're going to see the largest difference in the mean off here at the end. And the largest difference in the standard deviation is sort of at a 45-degree angle here. So magnitude 6.5. Magnitude 7, the difference, the largest difference here is 0.35 natural log units. And for standard deviation, it's 0.24. For the 7.5, you're only seeing the left side of the fault, so that it's bigger. And here now we're starting to see, in terms of the increase in the standard deviation, it's not off the ends of the fault where it's largest. It's actually within the boundaries of the edges of the rupture, so but near the edge of the fault. And we'll see this for the magnitude 8 as well, that it's not off the ends of the fault where we see the highest variability. It's actually within the fault, or within an RY that's less than half of the length. And in terms of the additional mean, it's highest off the edge, but it still can still be pretty large towards the ends of the fault. So then these are the reverse cases. So these are no longer pretty racetracks because the fault is dipping underneath here. So the racetracks here have a rupture distance that is the same, but because of the downward dip of the fault, it's no longer symmetrical on either side of the rupture. So for the magnitude, I'm sorry, oh, it's dipping down this way.
Jennie, is this half the faults or the whole?
This is the whole fault. This is a magnitude 6.
So why isn't it symmetrical off the ends?
Yeah, because I am off by like 0.1 on my site locations. So it's something I need to correct. And so there's circles there at 1 kilometer, 5 kilometers, 10, and 20, and then it's filling in the space in between. So I made my fault, I think I made my fault 10.1 kilometers long, something like that, instead of 10. But I did the spacing at 1 kilometer, so it's not exactly the same on either side. I just need to fix that.
So when you say it's 1/10 of a kilometer on one side?
Yeah.
Okay.
Okay.
So, so in the top one, the upward directivity, the top plot is the mean.
Yeah.
And you're getting an upward directivity pulse just above that blue thing, which is the fault. Is that right?
Well, so the fault is, this is the top of the fault.
Okay.
And then it's underneath here.
And does the fault go to the surface of the earth? Or?
It does.
I see. And so And then why is it smaller after the top of the fault? Just because the directivity pulse, you're off the directivity pulse pretty quickly because it goes all the way to the surface, is that right? So it turns blue again.
Over here, you mean?
No, above, at the top
Above
of the
here.
plot, yeah, there.
I'm not sure I understand why the pulses are strongest off here, off the edges of the fault.
And it's a pure thrust fault, is that right?
Yeah. Maybe Brian has an answer for this?
I think that's because in that area, the angles from between the fault plane and the direct wave is becoming so large that you don't expect directivity based on the theory. You don't expect directivity in those locations.
You don't expect directivity here?
Right. That's about 10 kilometers from
Yeah.
the top edge. Yeah. I think if you think of this in terms of Somerville's et al.,
Yeah.
that's where you're going to expect less directivities.
So we can think of it like a strike-slip fault on its side?
I can't remember what angle, the name of the angle that was in Somerville et al., but the phi angle, yeah, the phi angle is probably getting up to about 40 degrees, so
For this?
so you're not, yeah, you don't.
But so then why the peaks here?
Okay, the peaks is because there's, in the formulation, the length of ruptures toward a side also matters.
Okay.
So at that corner, if you have a hypercenter at the opposite corner, then you're going to see a lot of rupture toward the side.
Okay.
Okay, so that's why you have a peak along those diagonals.
So that's similar then to the strike-slip case of why you would,
Yeah.
okay.
Strike slip case, then the high will be located along the stripe because you're going to see what called it gun barrel, looking at the gun barrel. So.
Yeah.
I have a question and,
Yeah, Doug?
and a comment. So this is a fault that comes to the surface. Did you run cases that don't come to the surface?
I didn't.
Do you have a feeling for how that blue area would change if it doesn't? So if there is a Z-TOR of 5.
Not immediately, no.
And then I guess the comment that I would make is that the two red areas that are extending off at angle about 45 degrees, that's consistent with SH radiation for the reverse mechanism also.
Okay. Okay, well, I'm just going to keep flipping through the reverse cases then for you guys. So the 6.5, I guess the other thing to note is the hanging wall for most of these cases has a slightly negative or close to zero mean bias, but that is where the largest increase in the standard deviation is.
Jenny, one question.
Yeah, Gabe?
Your racetracks are now constant rupture distance, right?
Yeah.
And that's why they're deformed that way.
Exactly.
Yeah? Okay. And your sigmas are and your sigma is computed along each racetrack.
Yeah.
All right. Thanks.
Yeah, okay. So the magnitude 6.5, we're starting to get a change. The largest change in the mean is about 0.15 natural log units, and the largest change in the standard deviation is about 0.18. Similar for magnitude 7.
So I have a question here about the magnitude 7. This is a thrust fault, is that
Yes.
right? A long thrust fault. So directivity for for a thrust fault is really only up dip. And but you're getting big lobes off to the side. So this is a full calculation which has got the real radiation pattern. So I often run into cases where people look at things like the Chi-Chi earthquake and say, if the rupture is going north, I should see directivity. And of course, it was a thrust fault, and since the propagation velocity was perpendicular to the slip velocity, there is no directivity because the propagation direction is in the direction of a node. And when people looked at the Chi-Chi earthquake, if you look for directivity in there, you'll be hard-pressed to find it. You shouldn't find it because it's mainly propagating along the strike of the fault of a thrust fault. And I assume that effect is properly in here. Is that right?
Brian can perhaps answer this question better than me. It's because this is based on his model.
Okay, we look at how our model predict ground motion from the Chi-Chi earthquakes, and it shows looking at the residuals from the Chi-Chi earthquake, and it shows a pretty strong correlation between the residuals and our predictor.
But the prediction is a full finite continuum model of slip and predicting ground motion. Is that right?
Well, yeah, sort of, because we collapse the two-dimensional finite fault rupture into a line source for predicting directivity effect based on the isochron theory that Paul's footage developed.
But you do the radiation pattern.
The radiation
correctly.
pattern is part of the predictors.
Okay.
So there are three parts. One is the radiation pattern. The other part, the second part is the rupture distance toward the site, the length of the rupture toward the site, and also the directivity parameters that Paul called it the isochron velocities.
So it's important for everybody to understand that for earthquakes like San Fernando or earthquakes like the Northridge earthquake, that directivity is a big story. They're very clearly observed. But earthquakes like the Chi-Chi earthquake, where we have lots of records, directivity is really not part of the story in the Chi-Chi earthquake.
So this model isn't for a specific earthquake that has a given hypocenter. The idea here is we're kind of,
I understand that,
Yeah.
but
We're
when
smushing all those
people
together.
go to look for directivity in the real data,
Yeah.
because there's so many records available from Chi-Chi, directivity is not a big issue in Chi-Chi.
It's true that for those types of faults, the dominant directivity would be in the up dip direction, and it would be carried on the SV, by the SV wave field. But there is a weaker component of directivity along strike. It's not zero, but it is certainly weaker.
And
An example would be the San Simeon earthquake, which has the same sort of aspect ratio as Chi-Chi. And in that case, the Templeton record being large and the Cambrian record being small is something that is partly explained by by a horizontal component of directivity. But of course, that horizontal component of directivity is weaker than in the case of a strike slip fault. So I'm agreeing. I'm just pointing out that there is a non-zero horizontal component. It's just weak, relatively weak.
Paul, did you have a comment?
there were a few stations located up dip of the hypocenter of the Chi-Chi earthquake, and they do show more or less expectable directivity. And then as you go away from that, the effect sort of goes away. But I think the effect that Doug is talking about is just a kind of a time compression effect. You just have more energy arriving in a shorter amount of time if you have a long strike propagation. So the radiation pattern isn't helping you, but still there's some kind of accumulation, if you wish, of energy.
So this model and the pictures that you're seeing here are based on just one directivity model. and the way that it was chosen to be parameterized by Paul Spudich and Brian Cho. So this could be reproduced with a different directivity model, and you would see different pictures and different patterns. So depending on how strong the upduct versus a long strike, directivity was determined to be by that modeler. So this is just one way of looking at it. So I'm going to keep going. We can debate that for hours if we want, but I don't think that's what we're talking about today. The last case for the reverse, this is the magnitude 7.5, and we're still seeing these pulses off the end for the very, very long reverse case. And the large change in, or relatively large change in standard deviation over the hanging wall.
Jenny,
Yes.
you keep, I mean, you use the word change in standard deviation, but this is really
Additional, yeah.
additional
Thank you, yeah.
variability. It's not a change, we're not changing sigma by 0.16, it's
No, this is-
additional sigma we would RSS in with the
Yeah,
rest
I
of
guess
the-
this is where the sigma would be changed as opposed to areas where it would not change.
Yes.
Yeah. Thank you. Okay, so then using these forward modeling results, which I did from periods 0.5 seconds out to 10 seconds, you can make a model of the effect of directivity. The initial concept was to make a single model that combined these mean biases with the standard deviations about that mean. So it would be a simple thing that you would just sort of slap on to the standard deviations from published ground motion prediction equations, and you would move on. But after showing this at a few of the peer NGA-WS2 meetings, I decided to make two models instead, one for the change in mean and one for the additional standard deviation, so that you can look at them separately. That seemed to be what everybody wanted instead. So I went ahead and made models for both the strike slip and the reverse case for the change in the mean and the additional standard deviation. And the parameters that you need to know in order to do this are Rx, Ry, the width and length of the rupture, your closest distance, and the magnitude of the rupture. So in terms of additional calculations that would have to be performed, you would just, if you aren't already calculating Rx and Ry, then that is something that you would need to be doing within your hazard code. So for the strike slip model, I'm showing on the left the mean difference for a site that is 10 kilometers off the end of the rupture. So this is the site that's seeing all that huge forward directivity pulse that gets predicted. So this is the sort of the largest increase in the mean that is expected, or that's calculated from this model for the strike slip cases. The blue on there is for a magnitude 6. Sorry, you guys can't see. So the blue is for a magnitude 6, the green is for a magnitude 7, and the red is for a magnitude 8. And this has a scale from 1 up to 1.35. It's not log scale. I'm very sorry for those who wanted log scale. And then the additional standard deviation that you would SSRS into the ground motion prediction equation is over on the right. The blue here is for the magnitude 6, the green's the magnitude 7, and the red is the magnitude 8, and this peaks a little above 0.2. This is not the peak in the sigma, but it is the peak in the mean for the site right down the barrel, as we would say. Yeah, Jeff. Wait, you're gonna need a microphone. The units on the y-axis for this ratio between, sorry, thank you. The ratio between the standard, the spectral acceleration with and without this additional mean added onto it. This is the change, yeah, the ratio of change. So then what does this look like in terms of elastic response spectra? So I'm going to show you plots for a magnitude 6, a magnitude 7, and a magnitude 8. For the magnitude 6, the peak in the change is at 2 seconds. The red lines on here are without the effect of directivity, and the blue lines are with the effect of directivity. The solid line in the middle is the median, and then it's plus and minus 1 standard deviation. So for magnitude 6, not a huge difference. Magnitude 7, the peak here is out at 5 seconds. We're starting to see a little bit more of a difference. And for a magnitude 8, the peak would actually be beyond 10 seconds. So it looks like it's just going up forever, but it would actually curve back down out here. So for the reverse model, if we look at a site that's on the hanging wall and has an Rx of 5 kilometers, so it's 5 kilometers away from the top of the rupture, basically, and that has an Ry of a quarter of the length, so it's in between the middle of the fault and the end of the fault. Then we get changes in the mean that are all negative. So it starts at 1, and then it goes down to 0.95, not a huge change in the mean. And then the standard deviations will go up, up to about 0.16. So that's what you would SSRS. So that's a very small change in the total standard deviation, like 0.02, excuse me, not 0.2. So I'm only showing the spectra here for the magnitude 7.5. Basically, the blue lines and the red lines plot on top of each other there, so there's not a huge difference. If we then look at hazard space, I think Nick showed these this morning. So this is the hazard cases run for 1 second and 3 second at DCPP. The blue line in the middle there is the hazard with no directivity. If you add the mean model, the directivity actually goes down, or excuse me, the hazard goes down a little bit. And if you add the sigma model as well, then the hazard goes up slightly. Yeah, John?
Okay, so this comes back to a question I asked this morning. I think I know the answer now, but I'm just going to confirm it with you. So this morning, in seeing the same plot, I was surprised that the mean adjusted hazard curve was moving down. And I think the reason for that is they're just pulling off the mean from plots like what you just showed for a given location. Mm-hmm. Whereas what I am more used to seeing in past work is that the location of the hypocenter is a variable within the hazard integral. If you do it that way, it would almost always go up for long return periods, right? Because you're going to get sometimes the rupture coming towards you. It may be rare, but at long return periods that
So
would.
this is same. So for some sites, it would go up, and for some sites, it would go down. It doesn't necessarily. It does not depend on the return period.
John, what you're thinking about, the variability of the hypocenter, is in the standard deviation. So the model is randomize your hypocenter, compute the ground motion from, let's say, 10 different hypocenters moving along strike. What's the average of the change? And the variability. So you're thinking when you go into longer return periods, you're going to get the effect of the hypocenter being located down strike. That's the sigma. So we just partitioned the two. So what you're used to thinking about is actually only the sigma term, not the change in the median as well. Really is probably the way to think about this. There are some places where, on average, it would be larger. If you're sitting at the end of the fault, then you may be in a place in those maps you showed where even the median is high, and then we have variability about that. So we had talked earlier about combining these into one number like we're normally used to thinking about, and just say what is the sigma encompassing the mean value into the standard deviation, and we found that was not as informative as trying to separate these two pieces out. Does that make sense as to what?
Yeah, and you're not, in the actual hazard runs, you don't have a loop for location of hypocenter.
We don't need to because she's done
because
the work
it's there. Yeah.
on the sigma, right. We're just doing it outside to speed up the calculations of the big model.
But if I understood correctly, you had most of your hypocenters clustered near the, excuse me, near the middle. And so this would represent some sort of, almost like an average sigma, you know, in some sense. Because if you had a, let's say most of your hypocenters clustered at one end, would you have in fact seen a larger change in sigma as well as a larger change in the mean?
Yeah, if you used a uniform distribution for the hypercenter locations, then you would have seen a larger sigma adjustment.
Okay.
For us, it would be this, the source people would have to give us information different than the sort of average representation in our current data set. If they told us the hypocenters are clustered at one end or distributed, you know, more broadly in a different distribution, that could be incorporated,
Yeah.
but we need that information from the source characterization side. Ralph needs to say something.
Well, if this is a comment to the same problem, then go ahead.
It's a comment on the same thing that Norm was just talking about, which is that, but that would be in the source characterization something that you would normally see for reverse faulting, in the sense that you're almost always going to have up-dip direction with the rupture propagation. At long strike, I will agree that we don't know which direction it's going to go, and we can't, you know, you can't be sure of that. But generally what we find is that for reverse faulting, we would almost always see up dip. In other
And that's
words,
what I used.
And that's what you used. Okay,
Yeah.
that's fine.
So I guess my comment would, maybe this is more of a comment to Brian and the underlying methods. I guess you're using the Spudic's, what's it called?
The DPP one.
DPP
Yeah.
method, yeah. I'm just a little worried that you might be missing some important effects that would have shown up in a
in a
purely
different
dynamic rupture test, including more heterogeneity on the fault, for example, depth-dependent stresses in the reverse dipping faults. There's been several studies in various places that show that there's a correlation of, say, the heterogeneity of the complexity on the fault, either in terms of geometrical or stress heterogeneities and the resulting directivity effects, which I don't think would be captured in what you are showing. So I think just as a note of caution that there might be some effect that wouldn't be picked up in this effect here. Also, there's been some studies on including three-dimensional effects in the surrounding crust, which changes I guess it wouldn't be the conventional directivity effect anymore, but you could call it directional effects. You wouldn't get exactly the same symmetrical ground motion, whether or not the hypocenter is located in one end or the other end of the fault, for example. So,
Yeah, so I guess this model is only as good as the one that I use going into it. So Brian and Paul's, well, it's a great model.
Right.
But it's only as good as the one I use. And you would need epistemic uncertainty about this model to account for this, that there are other valid directivity models that you could have used.
So I just want to add that, you know, all this study is because we can't predict where's the hypercenter located on the fault plane for the next earthquakes. So can you imagine that we are required to predict the heterogeneity in the stress and slip distribution? That's, you know, that's for engineering application, that becomes a almost impossible task to accomplish, because we can't even figure out where's the, or predict with reasonable precision where's the hypercenter of the next earthquakes. So
I'm not saying you should predict the exact distribution of initial stress, but I'm talking about the complexity and the heterogeneity in the stress, which might be too simple in these models.
Yeah.
They might be too smooth.
I think Norm, if he was paying attention right now, would say that's a 10-year problem or 2 years problem. That's something we need to get to. I agree with you, Kim. But
Yeah.
now we use the
So I'll
models are
say
available.
too, this model was meant to be a stopgap measure that would be used for a couple years, and it's taken a year and a half to develop the stopgap that's meant to only last for a year or two. So, yeah, yes, it has those problems. Sorry.
Could you go back to the slide where you were showing the dip slip case?
What do you mean? Which slide?
Further back.
Yep.
That one.
That one.
This one, right. So here, the effect is largest for the smallest magnitudes, right? The mean difference.
The change in.
Right.
Yeah.
Which, and so this is good because, as we were just saying, if you have a small earthquake, and if your site's above, directly above the fault, then you're going to get forward up-dip directivity. Whereas if you have a very large magnitude, a long fault, then there will be less effect. Is this actually capturing that effect?
Say it one more time. Can you say it one more time?
What I'm saying is, we expect the effect to be the largest for the smallest magnitudes, as your result shows. Is that because you are capturing the effect that I just described, that for a small earthquake, sites near the fault are going to be getting up-dip directivity, whereas for a large fault, many sites, as in Chi-Chi, will not see up-dip directivity? Is that being captured in the way you're modeling directivity?
But part of this is what's in the underlying model already,
Right.
I think, right? Because if it's already there.
We're talking about Brian's model now, are we?
No, but there are stuff that's in an underlying GMPE that if a small earthquake if most of the cases are rupturing up dip, it'll get built into our median model already, right? In our way we scale.
Okay, this is the median model without considering directivity effects.
Correct. Already gets it because we don't.
Yeah.
Because that's the dominant feature, and now this is the deviation
Right.
off of that model.
Yeah. Okay.
So one of the main observations about directivity is that everything comes in phase. So we get a pulse, and sometimes they're called the killer pulse. And why do people call them a killer pulse? It's not because they're thinking about a linear system like a single degree of freedom response spectra for it. They're thinking that one pulse hits your building all at once, and that it now has some nonlinear response that has to deal with all those things coming in phase. And that can't really be very, very well captured by a response spectral kind of analysis. You almost have to go back to broadband time domain methods to do that. And I think it's an example of where we get into trouble trying to describe everything in these response spectra. If we were going back to the time domain, I think if you were in a tall building, you'd definitely want to know if a killer pulse was on its way to your building. But in this kind of analysis, it's not quite so obvious.
I agree that pulses should be handled by time series instead of the elastic response spectrum. And I don't think and for this case, we're not really looking at long periods. They're not the most important cases, so. Any other questions? Okay. Last slide then was the effect on hazard at 3 seconds, which Nick already showed you this morning. And then conclusion, right? So I showed you guys a model for both the change in the median, the mean, and the additional standard deviation that can be added to a ground motion prediction equation. We already touched a little bit on the idea that you'd want to add some epistemic uncertainty to this model because there would be other valid directivity models that could have been used to do something like this. And these are all going to be, these models are going to be published in a peer report this year. And that's it.
John?
So I think some of your plots were showing that the effect of the directivity on the spectrum would peak at certain periods, depending on the magnitude of the earthquake. Is that just a natural outcome of the way you did the analysis, or is that because
it's
Brian's model is a narrowband model?
Yeah, Brian's model is a narrowband model.
Okay.
So this mirrors his model in many ways.
The idea of narrowband model is not new. I mean, Paul has done some work on it more than 10 years ago. And Jack has did some work on the directivity power. So in the past, we assumed that directivity effect, regardless of magnitude, would just keep increasing as the period gets longer. So if you ask Paul's footage, he will tell you that this is one of the big achievement of the WS3 directivity working group, is that we bring in this concept of narrowband directivity model that reflects better the theoretical understanding of the directivity effects.
So just following up on that, some directivity models are narrowband, other directivity models are broadband, even within WS2, right? Only one. Mostly narrowband, okay. But the reason I mention this is as we think about epistemic, do we need a branch on a logic tree that would be for a broadband?
I think the answer would be yes, if it matters enough in the hazard. And so we're seeing in the hazard it's 30%, which is probably one of the bigger effects. And my guess is that we are going to have to build alternative models in terms of how we want to capture that. I'm not sure it has to be broadband versus narrowband, as long as in the context of the model we use, we broaden its range so that it encompasses the outcomes of those. So that's our approach needs to be to capture the range at the end. Not every model is captured, right? And so we can find some simple ways to do it. But I think the sensitivity is showing us, yes, this is one that we're going to have to add broadening or add epistemic uncertainty to it.